As our first real numerical method, we learned about approximating derivative at a specific point. And we learned quite a lot, but we actually left open the key question, one of the key questions of numerical analysis. It goes like that. You are trying to find an estimate of a derivative at a specific point of a specific function. So you choose a method, let's say the forward difference method or the central difference, and you obtain a number, which of course depends on the step that we actually used for this experiment. So we get some approximation. Key question is how reliable it is. What is the error of this approximation? Now we studied the error of the forward difference, central difference, and so on, but the answers that we obtained were general. We got answers about the order. So we know some estimate with some constant c, but we do not know the constant c. It's different for every example, for every experiment. And that's a key question of numerical analysis. It's one thing to actually find a way to produce those estimates, those approximations, but then it's another thing to ask about the actual error of this particular approximation. How do we find the error if we do not know the precise answer? That's a key question of reliability, and there are some approaches. And today we will look at a very specific approach, which actually is rather general. So for the moment, let's forget that d is a derivative. Let's just imagine that it's some value, some number that we are trying to approximate. And we have a procedure, and we don't care what procedure it is. It's just a procedure which actually works with a step size. And depending on the step size, it produces an approximation of this d of a specific quality. Now, furthermore, let's imagine and let's assume that the error of this approximation depends on h, and it is roughly dependent on some pth power of the step size. So that's what we called an order. So let's assume, in other words, that we know the order of the error. Now, how do we find about the actual error? There is an interesting trick. Let's have a look at the picture. Here's the value d that we are trying to approximate. And our first approximation is, let's say, here, dh. And here is the actual error that we are trying to find. Now here comes an interesting idea. I will make another experiment. I will get a test value, test approximative value, which I do by running the same procedure but with step 2h. Because the step is larger, I can expect worse quality of approximation, so it could be somewhere here, d2h. And this, let's say, auxiliary approximation has its own error, but the question is how large is it? And because we know the order of the error, we can also easily calculate that the error with step 2h should be 2 to p times the original error. Now, if you do not recall the details, here is how it goes. I'm substituting step 2h instead of h. So this is what is happening. And I can factor out 2 to p. And I get 2 to p times the error for the step h. So if the error of my original attempt is e, then this error should be actually the original error multiplied by 2 to p. Here we go. So we are getting a picture. And what do we see in this picture? Well, there is one more thing that we can ask about, this distance. How much is it? Well, first of all, this distance is simply dh minus d2h. But I can also obtain it by taking this huge error and subtracting the actual error that I'm looking for. And now you can see what's happening. I can factor out this e and then divide by this bracket, which is left after factoring out. So the error is approximately dh minus d2h divided by 2 to p minus 1. And that's a formula which allows me to approximate the error of my approximation of d based on another test run of my method with a double step. Now, This looks actually fairly easy, and one gets suspicious. Is it actually working? Because you can easily imagine, and this can happen, that when you double the step, the next approximation is farther, but to the other side of D. This could perhaps happen. So things would be totally thrown off the proportion in this picture. I couldn't use this little calculation anymore. So I think if you want to trust it, we have to do a more detailed calculation. So let's have a look at it. The value D is approximated by some experimental value based on a step h. Now, if I want to work mathematically, I would need equality, which means that I would have to put here precise value of the error. And if you go back to the experimentation or to the calculations that we did for derivatives, for the errors there, using Taylor expansions, things like that, the error typically has the following form. There is a leading term plus some tail, which can be estimated using another power of h. And this part is usually considered negligible, which happens when q is larger than p. So that's the basic equality that we are going to work with. And there are many, many numerical methods for which this formula is actually valid. As I said, this is not just about the derivatives. This is simply a general view of approximating some quantity using a procedure. And if for this procedure we have an error estimate of this form, then we are in for this game. Okay, now let's be generous. Let's not try just double of the step h. Let's simply multiply the step h by some constant a, presumably larger than 1 and presumably an integer. So we get the following, because this formula is supposed to be valid for all steps. So in particular, it should be valid for step a times h. What happens? Well, here we have c times ah to power p, and here we get o ah to power q. Another step. D is DAH plus, and I can factor out, and there will be a to power p times ch to power p. And this gets interesting now, when I multiply out, there is this tail actually, which is symbolically hidden in this O notation. And in all powers, I'm going to factor out a from the power, and this a to something becomes part of the coefficient. So it gets lost by this big O notation. It gets followed by it. This is simply O h to power q, again. And now we have two formulas. One of them is here, and one of them is here. And we can try to combine them in some way. For instance, we can take and decide to get rid of this h to power p for some reason. We don't like it. Because we do not know c. That's the key thing. We do not know c. If we knew c, things would be different. So how do I get rid of it? Well, by subtracting these equations, but then I also have to fix this part, this a to p. So I will take the first equation, multiply it by a to p, and then subtract it from this one, or the other way around. Which way do I want to play it? I think it will be nicer if I start with this one and subtract this one. I think it will be better. So let's have a look at it. I multiply this by a to p, and I subtract this one. So far, so good. I multiply this by a to p, and subtract this one. So far, so good. I multiply this by a to p, and I subtract, and it cancels. Great. I multiply this by a to p, and this is just a constant. Constant multiplies the tail. This should not change the order of growth or order of disappearance. So this big O simply swallows a to p, and it pretends that it's not there. And then I'm subtracting another O h to q. And when I'm subtracting two big O terms, we already saw it before, this just gets preserved. It will be another tail, but the rate of growth should still be h to q. Okay, that's a nice formula. And what do I see here? For instance, I see d. I can calculate how much is d by factoring it out and then dividing by the term. And I'm getting a to power p dh minus dah divided by a to power p minus 1 plus, and here when I divide by the constant, again it's a term whose rate of growth is h to q. What did we just obtain? We obtained a formula which actually provides us with approximation of the quantity d. And now how good is it? The previous approximation had quality CHP, so the error was of order h to p. But here the error is of order h to q, which is better. I will get back to it soon. But for now, let me do the finishing step. I'm interested in the error. So the error, by definition, for step h, is the actual value minus the approximate value. And now for d, I can substitute here. So it is a to power p dh minus d ah divided by a to p minus 1 plus OHQ minus DH. Okay, let's see. I'm going to connect these two parts using common denominator. And I get that the error for step H is, okay, common denominator is a to p minus 1. And what do I see there? A to p times dh is subtracted and added, so it cancels. Then it's subtracted, actually added, so there will be dh minus dah plus capital O h cubed. And that's interesting. Is it the same formula? The answer is yes, because if I double the step, then a becomes 2, and it works exactly. Now, here is a good question. There is an error. It's of order h to power q. Could it somehow overwhelm this information and make it useless? What is the error of my approximation dh? This error is of order h to power p. So this is O h to p, which means that this whole expression on the right is also of the order h to p. But this tail is of order h to q, which is something negligible when h is really small. And therefore, the majority of the meaning of this right-hand side must be sitting here. This expression over here must be also of order h to p. And this shows that for small step sizes, this error of error estimate is negligible. And this expression really provides us with a good estimate of the error. Now, this was a regular, proper mathematical calculation with capital O notation, and we know that it's proper, that it's okay. So this is actually a mathematical result. This is actually a very simple and a very powerful idea that can be applied in many situations. As I said, anytime you are approximating some value, and you know that the error can be captured by a pth power of h plus some tail, which is less important, you are in for the game, and you can actually apply this formula or perhaps this formula. I will get to it soon. Anyway, here comes an experiment. Let me just recall. When we introduced the forward difference and the circle difference for estimation of derivative, we took the exponential function and we looked at the derivative at 0, which of course is 1. So that was our test case. And for this test case, we were looking at the actual error that we can calculate if we know the answer and so on. So I'm going to do now the following. Over here, I have two formulas. The first one is this error estimate for the forward difference. Forward difference is a method of order 1. So for the method of order 1 and for a equal to 2, I'm actually using this formula now. When order is 1, it's 2 to 1 minus 1 in the denominator, so I'm actually dividing by 1. I can just ignore it. The error is approximated by the difference of these two estimates. And that's exactly what you can see in the first row, this DRFE. Okay, so DR stands for derivative, F stands for forward difference, and E stands for error estimate, if you are just curious about my notation. So this error estimate for the forward difference is just the difference of two experiments. The first experiment, as you can see, uses step size h, and the second experiment uses step size 2h. That's exactly to be expected. Then we introduced a better method, central difference, which is of order 2. So when you are using method of order 2, in estimating the error, we should use 2 to 2, which is 4, minus 1 is 3. There should be division by 3. Do I see it in the second formula? Yes, I'm dividing by 3. And what am I dividing? Experiment with h and experiment with 2h. That's exactly this, okay? So these are error estimations using this formula for the forward and central difference. And now let's compare the actual performance. Okay, so we can see the actual error, which is the red curve of the forward difference. And the blue one, that's the error that we estimated based on two experiments with this formula. And they are not quite the same on the right because their h is equal to 1. When h is equal to 1, then this tail can become quite large. 1 to q is 1, and so on. We talked about it earlier. But when h is small, these two estimates get closer. So let me focus again. Let me zoom in, and let me have a look at the range between 0 and 0.1. And as you can see, those two curves are now very similar. And if I zoom in still a little bit more, so the step h, the largest step h in the picture now will be 0.01. These two curves, they actually match fairly closely. You can see a little bit of red on the right. So there is really two curves, but they're almost matching. So in real life, in actual applications, this is actually a viable method of estimating the error. It works really well. Okay? Let's have a look at the central case, central difference case. So again, first an overall picture. The red curve is the error for the central difference, and we know that it's a method of order 2, so the error is no longer linear. In the previous picture, it was a straight line because it's a linear order of error. Here it is a parabolic shape, and again the blue curve is a little bit apart when h is large, but then the two curves, they get close together. And again, let me move in. I will focus, let's say, okay, let's not waste time, 0.01. And we can see a perfect match of two curves. It's a parabolic curve that fits a quadratic error for central difference. And this error estimate is really good. By the way, this is called Richardson error estimate. And we will get to this formula soon. This is called Richardson extrapolation. Okay? Anyway, the good news is there is a way to actually approximate error even if we do not know the precise value of what we are looking for. Okay? This is a very handy trick. Let's have a look at this one. As I said, this is another estimation of the value d, and it is of a better order. Sometimes when you are doing the analysis of the error, it may even happen that you are skipping some powers. So typically this q would be p plus 1, but it may be actually p plus 2, p plus 3. And if that happens, then the quality of this new estimate is markedly better than the original quality. But even if it's just p plus 1, it's still better than the original guy, than this dh. Okay? Notice that once you do those two experiments, calculating this formula does not really require much work. And for this little work, it's just few operations, you will get a much, much better estimate of what you are trying to get. So this is much less work compared to, let's say, going to much, much smaller h sizes, because when h is really small, you may have trouble with numerical errors, things like that. So this is actually a very interesting way to do just two experiments and then do a quick step to something really much better. This is also used in applications, and that's what is called Richardson extrapolation. Perhaps I should write it somewhere here. Okay, let's have a look at a picture and try to make some sense of it. So again, experiment. Here I have two formulas. One of them is for the forward difference, and the other one is for the central difference. And it's exactly the formula which takes two results and combines them together. So the forward difference is a method of order 1. So the denominator is 1. We talked about it. And here we have 2 to 1. So we're multiplying this experiment by 2. And I can see there twice the experiment with step size h minus experiment with step size 2h. Okay? 2h, by the way, is typical. It's nice to have a, but typically people use 2. Okay, for the central difference, we are dividing by 3. We talked about it before. The order of error for central difference is 2, so it's a better method. Okay, let's do some comparisons. Okay, what do we see? The red curve, that's the error of the forward difference. And we know that this error should be linear. And it seems here on the left, when h is small, that, yeah, it looks a little bit flat. The purple, or whatever curve, is the Richardson extrapolation applied to the forward difference. So we take the method which created the red error, and we apply this formula, and we get a new result which is of better quality. And it should be of order 2. So that's the purple curve. That's an estimate based on Richardson extrapolation and forward difference. And it really seems to be a much better method. It goes to 0 significantly faster than the red curve. The green curve, that's the error for the central difference method. And this method we know is of order 2. So the purple curve and the green curve, they should be roughly comparable in the way they go to 0. They need to be the same, because these are different methods. But they're both of order 2, so they should behave comparably. That's important. The last curve, the one down there, the dark navy there, that's the Richardson extrapolation applied to central difference. So it should be a method which is better than central difference. It should be of order 3. So the dark blue curve is related to the green curve, just improved using the Richardson trick. So do we see 3 different modes of behavior? Well, actually, here h's are really quite large, going all the way to 1. So this does not give a very good picture. Let's focus on, let's say, the range from 0 to 0.1. So we focus some more, and now we can see the difference between the red curve, which is the forward difference, method of order 1, and all the other guys that are of higher order. We can now see that they are not commensurable because the red curve is still significantly large, while the others are essentially gone. Would it help if we focus a little bit more, let's say to 0.01? Good question. And the answer is definitely now it's clear. We can see the straight line. That's the error for method of order 1. And the other methods are obviously of much better order because they just disappeared, their errors. Okay? So let's unzoom now again. And I'm going to do a little trick. I will remove the forward difference from the picture so that it does not interfere and so that it does not belittle the other errors. They will no longer be overwhelmed and forced to go to the x-axis or h-axis. Here we go. So now we can just see the 3 errors. The purple error and the light green error, these are those methods which we think are of order 2, namely the central difference, the green curve, and the purple curve is the forward difference, but improved by Richardson extrapolation. And they do seem to behave similarly. It's not like one would still be large and the other totally disappear. So they really are probably of the same order based on our experiments. But the third method, it did disappear already. So it seems to be of much higher order. Well, much higher means at least by 1. So this seems to confirm our guess that the third method in the picture now is of order 3, not just 2. Let's zoom in a little bit closer to 0. And let's see whether those 2 curves that are of order 2 start behaving differently. No, they are still behaving in a similar manner. They are both significantly large compared to the third one. So this shows that our appreciation or our expectations were actually met by this practical experiment. This all seems to work, which is a very good news. This Richardson extrapolation is a very simple idea, but extremely powerful. And we will actually revisit it several times in this course because it's one of the most, let's say, efficient tools for estimating the actual error that we make when we do some approximation. Okay, I think that's a perfect ending, so see you next time.